DuckDB under the hood. Module 1, why DuckDB is fast. We're going to start with a single query, watch it complete in 2 milliseconds, and understand exactly why that's possible. Let me start with a question. How long do you think it takes to sum up 5 million numbers? Not 5 million in a Python loop, 5 million integers in a database. Most people guess a second, maybe half a second if they're optimistic. Watch. I'll create the wide table. 5 million rows, 10 columns, real data. That took about a second. Now dot timer on, then select sum of revenue. 2 milliseconds, 5 million rows, one number out. That should feel weird, right? Let me show you how that's possible. Most databases you've used, Postgres, SQLite, MySQL, store tables row by row. Think of it like a filing cabinet where each drawer holds one row, every column glued together, ID, revenue, age, score, all 10, all on the same line. If you want the sum of just the revenue column, you still have to open every drawer and flip through every line because all the columns are stuck together. DuckDB does it differently. It stores each column separately. One file for IDs, one for revenue, one for ages, one for scores. Everything else lives somewhere else on disk. If you want the sum of revenue, you only read the revenue file. Everything else stays put. This matters because of how real analytical queries work. When you're analyzing data, you're almost never touching every column. You touch 3 out of 40, maybe 5 out of 100. Row storage reads all 40. Column storage reads the 3 you asked for. That's the whole difference. One more thing before we dig deeper. DuckDB is in process, no server. You don't start a database service. You don't connect to it over the network. You import it like a library. Postgres is a service running somewhere. Snowflake is a cloud. DuckDB is a file on your machine and a function in your code. Same process. That's what in process means. And it's why we can dig into the engine the way we're about to. Let's run explain on the aggregate query and read the plan. Read query plans bottom to top. Data flows upward. At the bottom is the sequential scan. That is reading the table. But look at the projections line. Only revenue. Not the ID, not the age, not any of the other 8 columns. DuckDB saw that you only asked for sum of revenue, so it only pulled the revenue column from disk. Above the scan is the projection node. It passes revenue through, nothing more. Same column, no transformation. At the top, the ungrouped aggregate. That is your sum operator. 5 million integers in, 1 result out. See how lean that is? The scan does all the work. Everything above it just accumulates. Now a point lookup. 3 columns with a filter. Let's see what shape that plan takes. The entire plan is one operator, a sequential scan. There is no index on AD, so DuckDB reads the table. But notice 3 things working together inside that scan. First, projections, ID, revenue, score. 3 columns, exactly what you asked for, not all 10. Second, the filter is inside the scan, not in a separate operator above it. DuckDB tests the predicate immediately as each row comes off disk. ID equals 999999 and discards non-matching rows before they travel any further. The scan does the filtering, not a separate node. Third, the estimated row count is 1. The planner knows this filter is highly selective and sizes the operator accordingly. One scan, column selection, in-scan filtering, and row estimation, all inside it. 3 aggregates at once. Let me run the explain and then the actual query. Watch the timer, 3 aggregates, 5 million rows, 5 milliseconds. Same shape as before, 3 operators, 1 pipeline. The scan at the bottom reads 2 columns, revenue and age, not all 10. Even though we asked for 3 aggregates, DuckDB only touches the columns those aggregates need. Count star needs no column at all. Counting rows is something the scan does as it runs. The projection passes revenue and age upward. Nothing else moves through this point. The ungrouped aggregate at the top accumulates all 3 numbers in a single pass. Sum of revenue, average age, count star. 1 operator, 3 results. That is the payoff when columnar storage and query planning work together. 1 read, 3 results. If you asked a row-oriented database for the same thing, it would read every column, all 10, because they are glued together on disk. DuckDB only moves the bytes it needs. That is the columnar advantage. Everything we just did, you can do it from Python too. Same engine, same speed. No connection strings, no server. 1 import. Call .sql, append .df. That is the method that converts the DuckDB result to a pandas data frame. Print it, and you get a standard data frame you can pass directly to scikit-learn, Matplotlib, Seaborn, or any other Python library. DuckDB runs embedded inside your Python process. The SQL executes columnar and multi-threaded, reading only the columns it needs. The result lands in memory as a data frame with no serialization, no round trip to a server, no connection pool to manage. For data engineers, this is how you drop DuckDB into an existing Python pipeline without changing anything else. The most powerful Python pattern: pass the file path directly into the SQL string. DuckDB reads only the columns the query touches, pushes the filter into the Parquet scan, and skips row groups the filter cannot match. The multi-file variant, star.parquet, works the same way across a whole directory. The rule: never load a Parquet file into a data frame before querying it. Loading first forces every column and every row into memory before DuckDB sees any of it. Let DuckDB see the file path. Module 12 demonstrates this on a million-row file where the difference is measurable. Here's an exercise. The wide table has 5 million rows and 10 columns. You're going to run 2 queries. Both return a tiny result, one number or one matching row. Before you run them, make a prediction. Which one is faster and why? 2 queries. Query A sums the revenue column across 5 million rows. One column read, nothing else. Query B fetches all 10 columns for a single matching row. Both return a tiny result. Make your prediction. Which is faster and why? Then pause here and run both with timer on. The exercise file has the full details and expected output. Your turn. The queries are on screen. Run them both with timer on, note the runtimes, then come back for the solution. Welcome back. Here's what you should have seen. Query A, sum of revenue, ran in around 2 milliseconds. Query B, all 10 columns for one matching row, took a bit longer, maybe twice as long, maybe 3 times. Both are fast because the data fits in memory. The gap is real though, and the explained plans show exactly why. Here's why Query A was faster. Look at the plan for select sum of revenue. The sequential scan at the bottom shows one column in projections, revenue. DuckDB read that column off disk. The other 9 columns in the wide table were never touched. Now Query B, same plan shape, but the sequential scan projections list all 10 columns. DuckDB had to read every column block to return that one row. More data off disk, more time. That is the whole story. You probably saw the sum query was faster, maybe 2 to 3 times faster. The real surprise is that they were both in the single-digit milliseconds. Wait until we load data bigger than your memory. That's when columnar storage earns its keep. 3 things to remember from this module. 1. DuckDB stores tables column by column. Queries only pay I/O for the columns they actually touch. 2. DuckDB runs inside your process. No server, no connection, no network overhead. 3. Explain is your friend. Read it bottom to top. Learn to see which columns are being read before you ever run the query. Next up, Module 2, Reading Query Plans. We're going to take those trees you just saw and learn to predict them before you type the query. By the end, you'll see a filter and know exactly where it'll end up in the plan.